Okay. I think I'm recording this meeting. Okay. Cool. Welcome guys. Welcome to the PHYS1A Lab Test 2 Revision Session. My name is Davide. Probably see me around the labs somewhere, or just living in this building, which I do. Please sign this. I'll give you like a few more minutes just to sign and grab chocolates. Please grab chocolates. And while we're getting started, do we have any preferences of topics to go through? Yeah, I got. Who did anyone? Who did? Whoever's here, they send the question about that weird like tube mercury tube question. You know what it is? Yeah. Okay. Yeah. So that's like literally the first one we're going through. Yeah, yeah, I don't know. When did you send it? Was like on the story. Yeah.
We texted it.
Yeah, I checked it. It was like, did you say weights?
Yes.
Yeah.
Okay. Like if we can like one question from like.
Yeah, I've got that pretty much in there already.
Okay.
So, I'm gonna put up here. So we had first that I don't like this color. No. Hopefully you can hear me. And then I'm gonna switch the mic up. No, you don't. Never mind. It's all good. Okay. Blue marker. Does anyone have anything specific they want us to go through or want me to go through? So I've got like that mercury question. You guys know what it is. We got like weight stuff. Now I haven't done this course in a while, and I don't teach it. Like I don't do PSWs. I did it like last year. I did PSWs. Is in like in waves. Is there anything specific? Oh, welcome. Anything specific in waves, guys? Want me to go through? I really hope in this space. Anything is yeah. You don't have to put your hand up. It's completely fine.
Yeah. Could you take questions that are specific to where they use like that really long wave equation?
Like with sines and cosines?
Yeah, the A what was it? A sine like
yeah, that's in there. So like y x t is equal to like a sine of k x minus omega t.
Okay, and
plus yeah, the plus is just like a plus c for sure. Like there?
plus 5.
Plus 5 in there?
Yeah.
Oh. That's just like a phase shift. That doesn't matter too much. But yeah, if you want to do plus c's over there, that's fine. It's just shifting up and down. Anyone else? Honestly, don't be shy. If it's like I don't watch it in lectures, fair enough. Like that's me for some of my courses for like a second. So don't worry about it. It's completely normal. How you guys feeling about like ideal gas law? Okay.
Oh yeah. Wait, is it not thermodynamics? There is, but like you cannot put down any. There's no being put down thermodynamics.
Yeah. I mean, yeah. We'll just sure. There is like a few. Like there is like that one is thermodynamics. That's a very specific question. A very weird one. But like PD plots, I think.
Sure.
PD plots, yeah, sure. If we get time, those aren't too bad. Pendulum?
Like how like this like that's a question.
In what type? Simple harmonic motion. Like yeah, I think that's a part of your I think that's part of the second half. Yeah.
And that's like at the end of it.
Yeah, that's fine. Yeah. If you wanna beat me the question, that's fine. Pendulum. I think I did some sort of pendulum question in the first half of this course. Maybe. I'm not too sure.
You did do a pendulum.
Did I?
Yeah, but it was more related to kinematics.
The one that's gone around.
Yeah, that one. Yeah, that's the spinning pendulum. It's
Oh,
like
yeah.
this pendulum.
Yeah. Because like pendulums kind of like super like small needles. Yes.
Oh no.
To go through the whole sheet. Just
Oh yes, that is a big one.
Oh, that's really smart.
As in like.
Just to understand what each
but like,
one is.
Yeah, of course. Okay. That might be like an interlude, like an English interlude.
Yeah. Or you just do the at the first and then do it.
Yeah. Maybe. Because there's a lot of stuff in the formula sheet, so like, if I do that first, I might have to speed run everything else. I like doing in the middle. I'll probably do it in the middle, that way I can get like a gauge of like how much time we had. But okay. That looks like the whole second half of the course. What's the last lab is like waves, which we got there. So, okay. Now, if you guys have any more suggestions, come up to this whiteboard and just put it. But also, again, grab chocolates. Come on. They are, yeah. Chocolates are good for your brain. Trust. Okay. Has everyone signed this, or at least? Cool. Hopefully. Okay. Now I'm gonna share my screen. So. I'm gonna do. Yeah.
I know a lot of this stuff from physics, so.
Whoa. 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 Yeah, guys. Devour it all. Honestly, devour it all. Okay. It'd be really nice to have a lectern, but you know, alas. How can I hold this? Yeah, I'll just set up here. Honestly, fair enough. Sorry, I'm like in your way, guys. My bad. I'm gonna be like right here. Okay, this is a long ass question, so like, don't mind it. Yeah, I've got my notes here. Don't worry, my mess. Handwriting is much needed than that. That was rushing. That was me rushing. Okay. Now let's get started. The first question. Okay, let's just mark this question one. A torsillion barometer, the type of barometer that has been in use since times of okay, a lot of yapping there. The important stuff. Yeah, like who cares about ancient Greeks are cool and all, but like this question, you don't need them. A tube is filled with mercury is okay. A tube with mercury is inverted in a dish of mercury. Okay, it did have a figure, but I didn't get the photos, so it's okay. I looked it up on the internet what this actually was. So this kind of looks like this, right? And it kind of looks like that roughly, sure. No, let's kind of like make it like that. It's a cylinder, so that's fine. Sure. Okay, and then it's filled up to some height, and then it kind of looks like that. Okay. So this is our barometer. What's filled in here is mercury. No. A barometer is just a name of a thing. Barometer means like pressure measurer, because like like isobaric. Like I think baro is like some sort of Greek or Latin word, yeah, of like pressure or something, whatever. But it's fine. You don't like literally when you speak this question, a lot of these words kind of like they throw you off. Just look the important stuff. Like that first line is completely irrelevant. Like, cool. Like that's just there. Like if you're interested, cool. Like.
Click here to read about it and you wiggle your time.
Yeah, exactly. Like, don't do that in test, guys. Please don't. It may, like, no, he probably won't give you a question where there's a link, but like, even if there is, that's just Tom being Tom. Love you, Tom. Okay, so we have this is mercury, right? and it's up to a height. Let's just measure height from like here, let's say, of H. Okay. Now, the height of the mercury in the tube is H in the diagram. Sure. Adjusts until the pressure. This is the important part. So adjusts until the pressure of the atmospheric pressure on the disc is equal to the pressure exerted by the weight of the mercury in the tube. Okay, just to say disc and tube. This is tube. That is disc. Is it K? No, C is British spelling, I think. Who cares? Okay, density of mercury is 13.56 grams per centimeter cubed at room temperature. Assume room temperature is in the following questions. Okay. Now, is room temperature really important? Maybe. Let's see. Okay, part 1. On days when atmospheric pressure is exactly 1 atmosphere, what is the weight of the mercury in the tube per unit cross-sectional area of the tube? Okay, so what we want is weight of the mercury per atmosphere, right? Or per area, sorry. Equals the literally, because that's what it is. It is weight of mercury in tube per unit cross section area of the tube. Now, also before we start questions, I always like to convert anything and everything into SI units. Just hate anything that's not SI units. It's gonna save your life. Like, I don't know if you've seen in labs, like when you do the Excel spreadsheet, you get like funky numbers. You're like, what's wrong? And like a lab demo comes up to you and go, SI unit, and walks away. Like, I've probably done that a few times. It's because it's true. Like, you have to like, if I see an answer like 1,000 times the normal value, I'm like, yeah, it's SI unit problem. So, let's just get these down. P of mercury, I'm gonna call it Hg, because Hg's symbol for mercury is 13.56 grams per centimeter cubed. Yeah. Now, the conversion to kilograms per meter cubed, just you can either take my word for it or actually get the calculation, is, I believe it's this. Yeah, this looks right, I think. Yeah, sure. That's kilograms per meter cubed. Now, the reason why is because to get from grams to kilograms, we have to do times 10 to the negative 3. To get from centimeters to negative cubed into meters to the negative cubed, we do times 10 to the 6. That's just because there are 100 centimeters in a meter. That's like 10 to the 2, and then 10 to the 2 to the power of 10 to the 3 is 10 to the 6, and then it's 1 over. So you do the other way around. So either way, we get like, and 10 to the 6 times 10 to the negative 3 is equal to 10 to, sorry, my handwriting. 10 to the 3, which is just times by 1,000. So if you want to go a bit slower and understand that in your own. Another 0? Oh, true. Yeah. Okay, fair enough. 0. Yeah, okay, cool, that's fair enough. Okay, yeah, so another 0. That's what I had in my notes, but I didn't trust myself, so I probably should. Okay, so yeah, take my word for it or think about it a bit. It's like, if you want to go in your own time and think about it a bit more, do so. It'll make you understand a bit more. But not important for this question. What was that? Yeah, like centimeters. Yeah, because like what I did, I just took the bottom straight away. So like if you want to go like centimeters cubed to meters cubed, you do if you want to do that, it's 10 to the negative 6, because you think about it, gets smaller and smaller, and then I just flip the signs. Because I flipped the other way around. Does that make sense?
Yeah, but what?
Here, oh, that's just because this part, yeah, because I go here and I go, well, like the first part, grams to kilograms, I'm doing times 10 to negative 3. And then the second part, I also have to convert centimeters cubed to meters cubed, so I have to do times 10 to negative 6. If I have like a number, say 1, and I do times 10 to negative 3, and then I times it again by 10 to negative 6, I get 1 times 10 to negative 3. Is that making sense? So like if I have like, you know, for example, like, yeah.
So just times 100.
Not really. No, it's just times by 1,000. It's just, you know, times by 1,000. Yeah. That's pretty much. That's why it's from centimeters cubed to meters cubed. You just times by 100 3 times.
Okay.
Yeah.
Okay, now
Okay, but in this question, we actually don't really need that because I'm just going to drag this down here. The force due to gravity per unit area. Let's just say area of the you know, cross set. I just say cross. It doesn't really matter what either of these are because I'm going to say this is called the pressure due to gravity, right? That's just P. That's not rho. That's just, I might make that capital P and lowercase p for pressure. Okay, that's pressure, right? But we know in this specific system, the height adjusts until the pressure of the atmosphere is equal to the pressure exerted by the weight. So in this system, this is actually equal to the pressure of the atmosphere, which is equal to 1 atmosphere in this question because we have atmospheric pressure exactly 1 atmosphere. Does that make any sense? That's probably like, I remember doing that question in like first year, and I was like, what the hell's happening here? But that's probably like the crux of the question. So it's all good. Does anyone not understand that? Okay. So the weight, here's the thing. In physics, weight is measured in newtons. So what this is saying, the weight of the mercury per cross-sectional area, that's just the weight of the mercury, so force due to gravity on the mercury, over cross-sectional area. And remember the formula, the general formula, like for pressure, is like force over area. Yeah, exactly. So you can, so then that's that equation there, which is equal to the pressure. Like that's the pressure due to gravity. But then we say in the system, the height doesn't stops changing when the atmospheric pressure is equal to that gravitational pressure. So then we equate them here. Where is it? Yeah, we equate them here. And then because they're equal, because that's kind of what the system is basically saying. Is that making sense? Yeah. Yes or yes?
pressure of gravity and pressure around this.
In this very specific case, yes, because the question says. Yeah, it is. Yeah, I remember. I specifically remember this question. I remember like when this person sent me this via email, I was like, oh my gosh, nostalgia. Like, such a good question. But yeah, no, it's good memories. But yeah, adjusts until the pressure of the atmosphere, adjusts until the pressure of the atmospheric pressure on the disk is equal to the pressure exerted by the weight. But yeah, so in this question, like we basically have, you know, atmosphere exerting on here, and then this height does not stop changing until, so this is like atmosphere. Right. And then that does not stop changing until the pressure due to the weight. So I'll just say pressure due to the, you know, weight is the same. Because you have like, you know, like the pressure on an atmosphere on like body of anything is just it just acts like that. Is that confusing anyone? No? Okay. Can we move on? Yes? Okay. Are you all good? Because that's why we're here. We need to understand. Yeah, okay, that's fine. Okay. Understandable. Honestly, like
Shut up.
Yeah, that is true. That is true. Although, yeah, always be prepared for questions like these because this is going to throw you off in the exam and you're going to be pissed. So don't get thrown off. Don't get thrown off. So a question like this will definitely appear. Probably not this question because, like, I don't know if Tom likes to recycle questions. Probably not. But something very similar could be because you get like a question bank. So I know you guys will get different questions. So like it could be there, like something similar to this. So like questions like these are always gonna like be around. Like there's gonna be like the questions where it's like, oh yeah, I know how to do that. Like hell yeah. And then there's like the last question of the exam is kind of like that question where you go like, what the hell? Yeah. There is transcription on this. So I don't want to swear as much as I did last time. I remember I was looking at the YouTube recording and it's like all like the swear words were transcribed. So I was like, damn, I can't swear that much. Okay, moving on. All good with that part. Okay, so I just do question 1. This is if this is part I, like part I or 2. Okay. Entire apparatus is now submerged under 1.76 meters of water with density. That's a density. What height does the mercury rise to? Okay, now in this question, we can say at a depth of 1.76 meters, and yeah, we know that the force due to gravity over the area, this is like the weight per unit area, is equal to just this, right? That's just Newton's law, right? But we also know that we know that the density due to anything like volume density is equal to the mass over volume because it's like mass per unit volume. Then I can rearrange. I can say mass is equal to rho v. But now let's not stop here. Now this is the cross-sectional area, right? Because it's force per unit area. I just say cross here. Now the volume of the tube, what is it in terms of H's and A's? Yeah, AH, yeah. Pretty good, right? And this is a cross. So something's going to cancel, like we can see. Mg on A cross is equal to rho H A cross on A cross. Cool. Ig, yeah, true. I mean, this can cancel, which is good because we don't even know the radius of this tube, which we don't even need it anyways. So that's why it's a good sanity check here, if that makes sense. Okay. Tell me this equation. Why did I start here? Is because we know that the force per unit area is just equal to the pressure. This is just, hang on, if I go here, that's pressure. And then, I'm just going to call that P. And then here is P as well. This thing here is rho, that thing here is P. Do not get them mixed up. I don't know, can you guys tell the difference between them two? Slightly? Yeah. One looks like a bit like weird. Okay. So that's the pressure due to the weight, right? But what do we know about this question? Pressure of the water, exactly. Wait. Now, what do we have here? Yeah. Which is equal to. So yeah. Maybe it's, well, now I'm thinking. Now the pressure of the water. Yeah. Okay. Equals to. What do we have here? No, my bad. Sorry, my bad. I've got you guys all confused. This is not, we're not talking about the tube anymore. This is just the disc. This is the pressure of the water. So this is disc. This is disc. This is like the mass of the water, which we don't know, but that's okay. We got rho here. This is rho of the water. This is rho of the water. This is not disc cross. Sorry, it's disc. My bad. I'm very sorry. I didn't specify that. Are we on the same page? Yes. If you guys don't know, honestly, let me know. Like, so I can actually help. Now, so that's all good, right? All good. So I just got that mixed up. So is everyone still following? Because we're trying to find the pressure due to the water, which is just like this thing acting here. So we gotta, use the area of this disc here, which doesn't matter in our case. We don't know the radius of that disc either. So, okay, we know the pressure of the water, due to the water. And when we calculate this, we're going to get, now, what do we know? So this is our rho here. So this is our H. That's our rho. And we know G is 9.8. Okay. So we know that in this question, rho is equal to, what was the value again? 1, yeah. Yeah, 1 gram per centimeter cubed, which is just 1,000 kilograms per meter cubed. Does that make any sense? Is that all good? Just because, like similar to before, I'm just timing by thousands. Is that all good? Yeah. Okay. Then we have, okay. So then in this case, P, then we have 1,000 times 1.76, because that's the height of the water, or height of the mercury, sorry. No, height, not height of water, sorry. Like how far is it down? How far is it down? And then we have times by 9.8. Now, if you trust me on this, I think if anyone wants to double check this, this is 7,248 pascals. We're not done yet, but we're halfway there. Is anyone still not following? Is everyone all good? Yes? Okay. So our question is, the reason why I wanted to find the pressure due to the water is because I need to find the total pressure acting on this system, so I can find the pressure due to the, so I can find the height of this, this apparatus here. Doesn't matter really. If you use 9.8, it won't make too much of a difference here, I think. Is that right? Okay, hang on, mate.
9.8 gives
248. Yeah, that's what I got.
20 something.
Look, if it makes that much of a difference in a question, they give you. Yeah. Look, yeah. If you like, I think in a lot of questions they have like a system where it's like error check how much it's off, and if it's like off by a certain amount, it just means you use 9.81. Like, it doesn't matter. If you use 9.8, 9.81, they won't mark you down because 9.8 is right. Now, what do we want? Okay, so we know pressure due to the water is equal to 17,248 pascals. Cool. So no, but then this is not the total pressure on the system because the system it's underwater. Not only has the water acting on it, but also has the atmosphere acting on it. So it's going to be slightly higher. In actual fact, it just adds up. So P total is P due to the atmosphere plus P of the water, which is pressure due to atmosphere was like what, like 101,325 plus the 17,248, and this will give you maybe if my calculator didn't fail me again, yeah, 118,000 roughly pascals. Okay, that's P total. you can fact check me on this. Now, now what do we know? We know that the pressure on the tube or on this system is the same as the pressure due to gravity from the mercury, right? That's the whole point of this question. So we know that pressure, this total pressure, is equal to the pressure due to gravity. So, what do we know? We know that force due to gravity on this cross-sectional or this cross-sectional area in this case is equal to P gravity, which is equal to P total, which is equal to 118,572. I'll just write it out again because why not? Now, using this equation, we know that the force due to gravity is mg on A. That's fine. We do a similar process to before. So this becomes Vg on A. And then, V is just A times H on A. These A's cancel, which gives rho Hg. So then, is everyone all good? All good so far? Yeah? Okay. So then I can say H, just rearranging. So I'm just going to say P total is equal to rho Hg. H is equal to P total on that's a very. Can you guys see my screen? Yeah. What would you rather, black or white? White. Black or white? Decisive vote. Doesn't matter. It just looks better. Yeah. Yeah. Okay, we gotta smash through this. We want to get as much. Oh yeah, sure, why not? Yeah, I don't want to stand like, are you there? Because like when the camera's on, it just like faces my backside. So I don't really want that view for the whole of the world to see. Okay. So yeah, you guys can still see. Okay, that's looking okay. Is this mic on? So I just got. Imagine if it's not. That'd be very awkward. No, please don't do that. Sure. Yeah, I think that's okay. Okay. And then this is rho G. Now we know from before rho was equal to what? Like something weird, right? No, rho was like yeah, like yeah. Rho was like 13,560. G's 9.8. Does anyone want to put that in the calculator just quickly? P total's this thing here. Yeah. Oh yeah. Yeah, I've written it there, but I just want to double check it. Didn't want to double check that. Not too confident with that. If it is, I'm happy. Oh, if you guys want more chocolates, are there any more? Okay, yeah. Literally just eat them all. Like, eat them all, guys. If you guys want to have some back, do you want chocolate? Oh no, wait, hang on. Wait. I need a different okay, so I need because I want what I'm trying to find is 18572 divided by 13. What was it, sorry? Oh, this is rho. Yeah, that's just rho, which means like volume density. So we got fraction 118,572 over 13,560 times by 9.8. Yeah, sure. Okay, so 13,560 times by 9.8. Yeah, which is like 0.892. Yeah, you're right. Okay. Oh, you already put in that. Damn. Whoops. I thought you were reading off that. That's why I was like, oh, fair enough. Yeah, I know. I think it could be. But yeah. Okay. That and meters. Don't forget your units. That is your answer for part 2. This question is a bit lengthy. We all good with that? Yes. This is all being recorded, by the way. So like, if you guys like don't understand, you can always just look back. But like, ask me as well because I can probably give better feedback if you guys don't understand. Okay, probably need another page. Okay, part 3. What was the question? Okay. The apparatus is now set up with a different liquid of this density, so slightly less dense of a liquid. Assume it's atmospheric pressure. So this system's not underwater anymore. It's just normal. What is a harder liquid? So it's similar question to before. Oh my. Similar to a question to before, we know that P atmosphere is equal to 101,325 pascals. That's an SI unit, so we're all good. Rho was 9.87 grams per centimeter cubed, which is 9,870 kilograms per meter cubed. Now it's going to be very similar to before. Like, this is a question once you understand, and once like you do the one part, the other part's just like replicating it. So in this part, force due to gravity, so the pressure is going to be like, if you like questions, it's just going to be the same as the atmospheric pressure. I'm just going to write that down straight away. Is that all good to do? Yeah. Okay. Which equals 2, and then I'm just going to write mg on A, which equals to rho vg on A, which is equal to rho hg. Is anyone all good if I just skip those explanations again? Or do you guys want me to go through? All good? Yeah? Okay. Now, rearranging H is equal to 101,325 on rho G. And according to my calculations here, I might go for them. 1.048. Which kind of makes sense. Because it's, it's less pressure. Is that making sense? Yes? Cool. That's the atmospheric pressure. Yeah, that's just formula sheet. I think, yeah, that's on the formula sheet. Yeah, okay, cool. Formula sheet. Which is, I'll just say for people, atmospheric pressure. Yeah, everyone just says like 101 kilopascals. This is a bit more of a specific value. I think that's given on your formula sheet. Yeah, they say 1.013 times 10 to the 5, which is the same. So yeah. Okay. All good for that. Yes. Let's move on. Question 2. Okay. This is a thermodynamics question. It's got Q's and stuff, so we already know an equation we can use. You can think about that while I explain the question. Okay, let's get started. A kettle has an output of 1,808 watts. Now, what does watts represent? Like what? Power? Yeah, okay. So we know that the power, this capital P is now power. So don't get confused. Power is equal to 1.8 watts, and watts is in joules per second. Yes. Oh yeah. This question. Yeah, sure. If you want to take a picture, go ahead. I might just zoom in. There we go. Yeah. So I'm like cutting back and forward. So like I just draw an image for now. So we know power is equal to 1,808 watts. Volume is equal to 1.14 liters. And which is equal to 1.14 times 10 to negative 3 meters cubed, because there's 1,000 liters in a liter. So, is that all making sense so far? Okay, and then temperature of the water is at 12.3 degrees Celsius. Now, just in case, we actually don't need it for this question, but it's just a habit. I always like to write down Kelvin just in case we need it. So, just for your interest, it is 285.45 Kelvin. That's Kelvin. Okay, we've got those values there. Okay, and T is equal to 11.6 minutes. And it's going to be useful to know seconds as well, which is 696 seconds. Okay. That's like the first thing I do, convert everything to SI units, just helps you out. Energy added to the water in 11.6 minutes. This is the first part. So energy added to water. This is the question. Okay. Now we know that power is the derivative of energy with respect to time. It's basically saying how many joules do I output per second. That's essentially what power is. Some people like to write it like this. Some people like to write it like this. In this question, probably the second one's probably a bit more useful because power is a constant in this case. So you can either do the integral way and just value integral, P's constant, so it doesn't really matter. In this case, I can just go P change in time is equal to change in energy. Now, all we need to do is multiply the power times by the time equal to 1808 because it's in watts. It's SI unit. Watts is joules per second, so we're sweet. Times by the seconds. So we actually need the seconds one. Which equals to, what did I say here? 12,058. Oh, no, not 12,000. 1,258. My bad. 0.368 kilojoules. I think, yeah. Or, if you want it in joules, it was like 258,368 joules. Is that all good? Yeah. Okay, cool. That one was not too bad. Okay, what's the second question? How much energy do you need to raise all the water in the kettle by 100 degrees? Okay, when you see adding energy to get a certain temperature in the water, you just think of specific heat of water. Does anyone yeah, because MC delta T. Because that's specific heat of water basically says how easy can I heat up the water. That's essentially what specific heat is. So specific heat of water is very high because it's pretty easy to heat up water. Think of boiling pasta or something. Yeah, pretty much. Yeah, oh yeah, is it? Oh yeah, true. Yeah, okay, never mind. Then the other way around. Yeah, more higher than. Yeah, that makes sense. Then yeah, but then I think it's normally I think it's higher it is the lower the I don't know. I'm just talking about my ass here. Okay. So other than that, we know Q is equal to MC delta T. If you remember this one, I just say Q equals MCAT. That's from high school. It's because that delta kind of looks like an A. But Q equals MC delta T. Now we know that the mass is 1.14 kilograms because going back to here, I just go over here, up here. Mass is equal to 1.14 kilograms because in 1 liter for water, 1 liter corresponds to 1 kilogram. That's just a standard unit of measure. So we know that there's 1.14 kilograms of water. Specific heat Now I used, what did I use? 4,000. No. Yeah, 4.1. Yeah, 184. Wait,
4,100.
wait. Does it have the unit? Because sometimes like 4.8, I think is in joules, and yeah, joules per kilo. Is it? Yeah, I think so. Yeah. Oh, yeah. No, sorry. So specific heat is 4,184 joules per kilogram per Celsius.
86.
Yeah, 4186. Because okay, yeah, I got it up here. Specific heat is equal to 4.186. I think it's joules per gram per Kelvin, which is equal to 4186 joules per kilogram per Kelvin. Does that make sense? Yeah. It's just, and you need to be very careful which one to use, because if your mass is in grams, use that one. If it's in kilograms, use that one. Otherwise, you get all messed up and you'll be off by. Is that making sense? Okay. Now delta T. Well, delta T is T final minus T initial. So this is 1.14 times by 4184 times by, now final temperature is 100 because we're trying to get it to 100 in this question. You guys can see that at the back. The question. Yeah. And then its initial temperature was 12 degrees, 12.3 degrees Celsius. Now, some of you might be thinking, well, the units for the specific heat and Kelvin, why are you using Celsius? It doesn't really matter, because Celsius is really cool because the change in Celsius is the same as a change in Kelvin. Like, 1 degree change in Celsius is 1 degree change in Kelvin. Unlike Fahrenheit, so Fahrenheit does suck. Yeah. Like, does anyone know the conversion formula to Fahrenheit? Was that? Hmm? Yeah. I'd say, why would you do that? Like, Celsius. Yeah, no, I know that. But I'm like thinking of that formula. Like, it's like, yeah, it gives Americans an extra step to do. It's like, for us, it's just like, it's so easy. Yeah, that's why Celsius is better. And then there's like another version of temperature as well, another unit of temperature. I can't even remember what it's called. It's just something disgusting as well. Okay. Yeah, scientists get bored. Okay, then you evaluate this, you get, I think, 418,307.952 joules. So that is the energy needed to raise like the whole kettle to 100 degrees. So now question 3 was, how much water is converted to steam? Now, how much water is converted to steam? Now we need a mass, so we need to find the mass of this steam. Now, how do we do this? We do this through conservation of energy. We know that over 11 minutes, like, this kettle doesn't turn off. So like after 100 degrees, it's just going to keep on boiling water and it's going to turn into steam. So the total energy is going to be the energy like Q plus MCL, because that's the latent heat of vaporization. Because it turns into water, and then water has heats up water and then turns into steam. So this part is heating up the water. This is for the steam. Now we know from part 1 that the energy was this big number, 1,248,368 joules. So I'm just going to put that in, 58368. And then I'm just going to minus the Q straight away from the other side, which was 418,307.952, which is equal to MSL. All good so far? Yes. Yeah. Okay. The silence scares me. So have some chocolate, guys. Have some chocolate. Keep you awake. It is Friday afternoon, so honestly, fair enough. That's fine. Yeah, that's fine. I'll just zoom out a bit so I can keep on going. Okay. Then I can go. The mass is going to be this sum. Well, this difference here. I'm lazy, so I'm just gonna copy paste it. Sorry, guys. Over the latent heat. Now, the latent heat is on your formula sheet. This is like latent heat of vaporization is like 22.6 times 10 to the 5 joules per kilogram. That sounds right. That's just a constant. Just take and leave it. What was that, sorry? That's total energy. So that's from part 1. That was like the energy like added to water over 11.6 minutes. No, yeah. He's just like, because the kettle has that certain power and it's on for 11.6 minutes. So how much energy is being transferred to the water? Assuming there's no like energy loss in like heating the kettle like material. I don't know. So times 10 to the 5. This is okay. I don't need to do any conversions because the things are already in SI units. That's why I say SI units are good. Now this you get roughly 0.3717. Yes, is that what you got? Nice. Okay, kilograms. That's going to be a mass of water turned into steam. Now make a box. Good. Okay. Any questions? No. L is just a constant in your formula sheet. It's called L is the latent. I'll just write it down. Heat of vaporization. That's the full name. Yeah, I think so. Yeah. Oh, is it? Yeah, maybe one of the two. Yeah, latent heat of evaporation, vaporization, essentially the same thing. I'm pretty sure. Because it's like you got the latent heat of fusion, which is like when ice turns into water, and then you got like latent heat of vaporization when water turns into steam. Because water vaporizes to turn into steam. Because vaporize. Is that making sense? Yeah. Cool. Yeah, it's just a thing on your formula sheet. I put roughly the same thing. I rounded it a bit, but it doesn't matter. But making sense? Yes. Okay. Yes. Yeah. Exactly. Because it's total energy. So you do energy like conservation of energy. So energy in is equal to energy out kind of thing. Yeah. So no, not a whole. Yeah. So we basically found how much energy is going. Like we're basically saying how much energy is going into the kettle, which is because it has a certain power and is left on for 11 minutes, so a certain amount of energy is going into that. Then we say all this energy is going into first heating up the water. How much energy is the whole 11 minutes and 6 seconds? Yeah. 0.6 minutes of it. Then we found out how much energy of it was put into heating up the water. Yes. And then the remaining of that is going to be how much energy is put into turning it into steam. Exactly. Yes. Perfect. Yes. Exactly. That's good. Okay. Basically, like, what's the energy? Like, how does this equation work? Like this one here. Like I was saying before, because you got total of E amount of energy going into the system because the kettle is heating up the water, for a certain amount of time because power times by time is energy, like power over a certain period of time, and then that energy is first going into trying to heat up the water. But then after 100 degrees, the water starts turning into steam. So it's like the energy has nothing else to do but start turning water into steam. that's where this part comes in, that MSL, and starts trying to boil the water. And then, but that, because like MSL is like the energy required to boil, or like not boil, steam a certain amount of water. Is that making sense? Cool. Okay. Any questions? No? Yes? That's fine. Yeah. If you want to take a photo, you can. Yeah. Okay. What time is it? Okay. It is. Okay. Too late, Anna. I was like, Anna, send me some more wave questions, and she just sent them now. It's okay. All right, we'll have a bit of an interlude. We'll have a 5-minute break, and then when we come back, we'll go through. We'll just Hello. Hello.
It's not too bad.
Yeah. Yeah. So yeah, my iPad just died, guys. So
Maybe just that's the end.
yeah. Well, I mean, that was like the end of that question anyway. Thank you very much. That was the. Oh, it did transcribe, guys, because the transcribe's on this screen. Yes, guys. Okay. So yeah, my iPad died, so that's why I turned on the mic on this one. So I'll end the recording now. But you guys saw that final equation on the iPad. It's just that double, that kind of that two brackets, and then that F is like the original frequency. That's just because you apply the Doppler effect twice, like we did. Like, you know, you apply it like the first part and you apply it like the second part. Thank you guys for watching. Good luck with your test. No, how do I stop? Oh yeah, I don't know if I'm recording, but it's okay. It's recording. Okay, so hopefully that recorded the last part, but I won't. Anyways.